Hello, everybody, and welcome back to my second talk on the homeomorphism problem for hyperbolic manifolds. Let's jump right in. So, in the previous talk, we saw evidence that the perspective of Gromov hyperbolicity of the fundamental group and the perspective of manifold theory were kind of insufficient for understanding this bounded runtime solution to the homeomorphism problem. And so this time I'm going to showcase a different perspective, one that takes advantage of the combination of hyperbolic and manifold. What hyperbolic manifolds are can be thought of as defined by the lattices in Lie groups. In particular, these Lie groups are groups of matrices, in fact, and that's going to be really useful. So, if you're scared of Lie groups like I am, I'm a combinatorial topologist. I like triangulations. I kind of like the geometry of hyperbolic manifolds, but Lie groups scare me, and we're really going to be using tools that come from Lie groups without having to fully understand the Lie group theory that goes into them. So don't be scared off if you're scared of Lie groups, and I'm sorry if you're not. We're not going to be talking too much about Lie groups. So the outline of what we're going to talk about today is a result by Grigoriev and Vorobyov that tells you that if you have a system of polynomials, then you can find solutions to that system of polynomials which are bounded as a function of the size of the system. Okay, so alone it doesn't seem particularly relevant, but what we're going to see is that these geometric triangulations that we're searching for, they're really linked up with representations of the fundamental group. That somehow, especially if you're just looking for a one vertex triangulation, geometric triangulation and representations really go hand in hand. And then we're going to see that, well, representations, they naturally can be thought of as solutions to systems of polynomials. So if we've got ways of bounding systems of polynomials, we've got ways of bounding representations, and so we've got ways of bounding our geometric triangulations. Now, a problem that you might have with that, if you already know something a little about representations and how you would find them as solutions to systems of polynomials is, okay, big deal, you can tell me that there's a representation and that it's bounded. Well, I could already do that without any fancy algorithm. The trivial representation of a group, just send everything to their density element. Surely whatever definition of bounded you're using, that's going to be bounded. And so what we need is that the nice representations that do everything we need them to do, that those can also be found by this system of polynomials approach. And we're going to do that using rigidity results. This is where the big lattices and Lie group stuff comes in, that show that the nice representations play nicely with the system of polynomials. And the big moral of this whole story is that polynomial systems of polynomials can give geometric control over lots of different aspects of the geometry of hyperbolic manifolds, as long as you can, through many different tricks, talk about them in terms of polynomials, you can control them. And admittedly, you can only control them within this like quite big bound, but if that's all you care about, you can do a hell of a lot. So we'll come back to that in a minute. But first up, let's talk about systems of polynomials. So really, this is just, I just want to make the technicalities of this result clear. If you think about a system of polynomials, you can think about the size of that system. And the size of that system is for Grigoriev and Vorobyov's result determined by the number of polynomials in your system, the number of variables that the polynomials are in, the maximal degree of the polynomials. So this is the maximal degree of a monomial, really, in these polynomials, and the degree of a monomial is the sum of the exponents. So x squared y, that's degree 3, for example. And then the maximal complexity of the coefficients. The coefficients are going to be rational numbers, as you can see here. And so a rational number is just the sort of bit length of the numerator and the denominator. So 90 divided by 91, that's like whatever log2 of 90 is plus whatever log2 of 91 is. That's your that's the complexity of that, the coefficients. Okay, so if we can bound all of those things, then we have a sort of bounded size system of polynomials. Furthermore, these are polynomial inequalities, so you can have even strict inequalities or non-strict inequalities, and non-strict inequalities means you can also have equalities. You just say polynomial greater than or equal to 0, polynomial less than or equal to 0. For polynomials with rational coefficients in these variables. Okay, so that's how you describe the size of your system of polynomials. And Grigoriev and Vorobyov said that if you're given a system of polynomials and you can describe its size as above, then there's an algorithm which runs in time polynomial in this quantity, which is sort of exponential-ish in the size of the system. Then for each component of the solution set, this algorithm provides you with a solution. And not only does it provide you with a solution, but the solution itself has its size bounded as a function of the size of the system of polynomials. So the absolute value of a non-zero entry in your solution is bounded in this way, so sort of doubly exponential in the size of the system. And in fact, you can bound 1 over the variable in exactly the same way. And that means that this bound is sort of on both sides. It would look slightly different on the left, and so I've not written it because I don't want to confuse you, but really it's of the same order. On both sides, you get a bound above and below on all non-zero entries. So as long as you confirm that something's non-zero, you can control its extremities. It's not too big, it's also not too small, and that could be very useful for controlling the geometry of your space. You don't want tetrahedra, for example, that are too big. You also don't want them that are too sort of flat and stretched out, maybe. Okay, cool. So that's the big tool we're working with. And before we can do anything with it, let's first talk about how our geometric triangulations are going to relate to representations. So I'm making a simplification here. We're looking only at one vertex triangulations of manifolds, and here this manifold admits a hyperbolic structure. The multi-vertex case is handled, instead of representations, it's with cocycles into the same group. I didn't want to have to define cocycles and talk about the sort of tricky fiddly stuff that happens there. It's really the same. The essence of the argument, again, is the same, and so we're just going to talk about the representations case. So what does it mean for your manifold to admit a hyperbolic structure? You've got this topological triangulation over here, and you've got a homeomorphism to this hyperbolic manifold, which is the quotient of Hn by some lattice. And because it's the quotient of Hn by some lattice, this homeomorphism is inducing an isomorphism between the original group and the lattice. And that means that the lattice is actually a faithful lattice representation of the fundamental group of our manifold in the isometry group of Hn. So because we started with a topological triangulation, then we end up with a fundamental domain. I've drawn it here as if it were the fundamental domain for the action of z squared on r squared, which is not hyperbolic, but you end up with a fundamental domain for this. You end up with a triangulation of the universal cover. Because the topological triangulation, you've got no control over what these edges look like. You know their start point and their end point, but they wobble around in the middle, and because of that, so do the two simplices, and so do the three simplices, so do the four simplices. They're all homeomorphically embedded, but their images are these floppy, non-geometric objects. Okay. Except that's not true for all the simplices. If you look at the zero simplices, labeled here, imagine A is our chosen lift of our vertex, and then B is B, C, D. These are all the other lifts. Well, where B, C, and D are determined by the representation. So they're determined by the lattice. You've got a representation, and it takes this gamma, this edge, which maps down to a loop. That means that your representation takes this gamma somewhere. That's an isometry of Hn, or in this case of R squared. It takes A to B. The same gamma prime gives you an isometry taking A to C. Gamma prime prime gives you an isometry taking A to D. And so the vertices, picture on the right, the placement of the vertices of our fundamental domain is determined by the elements of the deck group, but the deck group is a lattice. So the vertices, in this way, they retain the information of the lattice. Okay, so what we're going to do, and the lattice kind of encodes all of the geometric information about the manifold. So what we're going to do is try and use the lattice to straighten the triangulation, to make ourselves a geometric triangulation. And you can see this picture here of what it looks like when we straighten out all the edges. So we take our top dimensional simplex, this 2 simplex ABD, and we replace it in this universal color by a geodesic simplex, by the convex hull. So the edge from B to A just becomes a straight line, from B to D becomes a straight line, from D to A becomes a straight line, and then everything in between becomes a geodesic 2 simplex. And that's what we've ended up with down here. And because we're doing all of this in the universal cover, these the straightened simplices are unique. There's only one convex hull of these points. It's the convex hull, not a convex hull, right? Exactly. So I've made it look here. I've kind of cheated a bit here. The topological triangulation I picked, when I straightened it, it gave me a geometric triangulation of the torus once we quotient it out by z squared. But you could have some problems. So if you see, this could occur in your situation where you have a topological triangulation like this, and this is where the points lie in the universal cover. And then what happens when you try and straighten this picture? Well, here's the 2 straight triangles, and they've got some overlap in the middle. And so that's a problem. So when we straighten our topological triangulations in this way, we get something that's geometric now. It's sort of a cover by geometric simplices. It has this nice map in from the original topological triangulation, but these overlaps mean it's not a triangulation itself. And so I don't have time to go into the details, but what you can do, I mean, you can see in this picture how you would get a geometric triangulation out. You simply subdivide each of the simplices, so you get one triangle here, one triangle here, and one triangle here. And then there's no overlap anymore because we've sort of replaced the overlap period by its own geometric triangle. And I said I'm not going to go into it, but what we have to control to make that all right is how many of these overlaps can you have and how bad can they look. And that's something that if you have control over the geometry of these simplices, you can control the number of the intersections, and thus you can control how many overlaps there will be and how many geometric triangles or n simplices you'll need in the eventual form. Okay, but so imagining we've got all of that sorted out, and we're happy going from this topological triangulation to this straightened geometric triangulation. Note that this straightening doesn't depend on the homeomorphism that you started with. It only really depends on the topological triangulation and the representation of its fundamental group that's induced by this homeomorphism. So what do representations induced by homeomorphisms look like? Well, they look like faithful lattice representations of the fundamental group. So we don't need to, so the problem is homeomorphism, you can't have an algorithm find you a homeomorphism because they're almost impossible to define homeomorphisms in an algorithmic way. Because they're so floppy, because there's so many little deformations I could do to this drawing, you can't define it. You need a sort of finite data that can describe what's going on. Well, where the vertices go, that is finite data. And that's all we need. That's all we need to define this this straightened triangulation. Okay, so that means what we're searching for are the sorts of representations induced by homeomorphisms. We're searching for faithful lattice representations. So yes, again, unfortunately, we don't get a triangulation at the end, but trust me, we can make that work. And as long as we have control over what the geometric thing looks like, then we have control over how complicated the geometric triangulation we get out at the end is. So that's what we're going to see coming up, is how do we get control over the geometry of this straightened triangulation thing that we get out. Okay, so we're now here, we're at how to, we've got from geometric triangulations to representations, and we know that if we can get to systems of polynomials, that we can bound solutions to that. So how do we do that? Okay. So given a presentation of the fundamental group of our manifold, and remember, how do we get this presentation? Well, you've given me a triangulation, and especially if it's a one vertex triangulation, then the generators are the one simplices and the relations are the two simplices. Then a representation into SO plus N1, this is a matrix group that's isomorphic to the isometries of HN. Well, that's given by, for each generator, you just define a matrix of variables xi, so that's n plus 1 squared variables, and a matrix of polynomials that says xi is actually in SO plus N1. I mean, this is where we use the fact that SO plus N1 is defined by a polynomial relation. And then also, so for each variable, we've got this thing that says it's in SO plus N1, and we also have polynomials for each relation. So polynomials representing what it means to say that these two matrices, when you multiply them, give this final matrix. But again, it's only one polynomial for every entry of the matrix, so only n plus 1 squared polynomials. Okay, so you can see from this that we get a system of polynomials, and well, what are solutions to the system of polynomials? Well, it defines a map from this group, this presentation, to this group of matrices, where the images have to satisfy the relations. But that's exactly a homomorphism, and this is exactly a representation of this group in SO plus N1. So that's what our solutions are. And remember, I mentioned it earlier, to perform our straightening, we're going to need representations which are faithful, and we're going to need representations whose images are lattices. So it's all well and good, we've got a system of polynomials, but what if the bounded solutions we get out from Grigoriev and Vorobyov are simply the trivial representation, or they're a representation of a different lattice that's covered by our original lattice or something like that. That's the worry. But fortunately, everything's okay. So there's a rigidity result. So this is the big lattices and Lie groups thing that I was talking about earlier. There's a rigidity result that says that all faithful lattice representations lie in their own connected components in the variety of representations. So what that means is that all of these solutions to the system of polynomials, remember, we get bounded solutions in every connected component. And that means we're going to get a bounded solution in the connected component corresponding to the faithful lattice representations. So we now know that Grigoriev and Vorobyov's algorithm gives us a bounded faithful lattice representation. Now, before I move on, I should say this is a tiny lie. This is true for closed 3-dimensional hyperbolic manifolds, and it's true for finite volume 4 and above dimensional manifolds. In the cusped 3-dimensional case, you have to require that your representations send parabolics to parabolics. That's possible. You can add it into your to the system of polynomials up here. I just didn't want to go into it because it's a real specific subcase. Okay, but so that tells us that we've got this bounded faithful lattice representation. And so, and we're using our representations to give us geometric triangulations. So the boundedness is, so we've got boundedness of geometric triangulations. But you might think, okay, well, you've got a bound on this lattice generators, for example, how does that give you a bound on like concrete facts about your geometric triangulation? And this is the sort of the big trick, the big powerful thing that we can do is we can sort of sneak in the back door and make it so that our solutions contain a bunch of geometric quantities. So what if we added in some useful variables corresponding to geometric quantities of the manifold? For example, the length of an edge of one of these straightened out simplices, that's simply the distance between its endpoints, which for a certain model of hyperbolic space is just log of a polynomial. So it's almost a polynomial, we can almost shove it straight in. But so if we just set a variable EL for exponential of length, set that equal to P, then we know that e to the length is equal to P, that's just true. And so we can just add this polynomial and this variable into our system of polynomials. It's barely changing the size of our system of polynomials. And then Grigoriev and Vorobyov say, okay, you get a solution out where edge length is bounded in this way. So e to the length is bounded by 2 to the 2 to the big O n to the 4t. And so the length is bounded by 2 to the big O n to the 4t, approximately. And so that means we could do that for all the edges. And we'd have all of these geometric n simplices, and we know exactly what range all the edge lengths lie in. And in fact, we can do similar tricks to this. Note that we didn't have to start with a polynomial, just something that we could fiddle with until it became a polynomial for different geometric quantities of the manifold. You can do it for angles and you can do it for the volumes even with some trickery. You can get lower bounds on things, you can get upper bounds on things. It's all about whether or not you can word it in terms of polynomials. So that's really exciting. That's some geometric control that we get over it. So here's a summary of how this all works. Grigoriev-Vorobyov's result on systems of polynomials, along with the rigidity results of Calabi-Vallée and Garland-Raganuthan, they prove the existence of a bounded faithful lattice representation. We then play around with this system. We add useful variables corresponding to certain geometric quantities, such as edge length. And then we look at the geometric triangulation that's induced by this lattice. And thanks to our useful variables, we have control over its geometry. All of our variables and all of this control is bounded by a function of the dimension and the number of n simplices in the original triangulation. And that's because it's all bounded by how many variables you started out with, or it's bounded by the number of edges you want to bound, or all of this, or it's bounded by the number of generators in the presentation. And all of that is determined by the size of the original triangulation. Okay, and so that's where we get these bounds on runtime from. So a reminder why this is useful: to solve the homeomorphism problem in bounded runtime, we saw that there already is an algorithm, at least in the closed case, and I believe it can be adapted to the cusp case, that it was possible to compare geometric triangulations with this algorithm. And the time bound was a function of the size of the triangulation and the complexity of its geometry. And so the techniques described above give you a geometric triangulation whose size and geometric complexity are bounded as a function of the size of the original triangulation, which is just this combinatorial information, which tells you that you can, if you're given two topological triangulations, you find their bounded geometric triangulations and then apply Queller and Fanz's result to those bounded geometric triangulations, and you get a bounded runtime, because it's bounded to get here and bounded to compare them, algorithm for the entire homeomorphism problem. So the moral of the story here, I've been vague on the details because I wanted to show you this big moral, which is that you can translate a lot of geometric quantities of your manifold into polynomials in a system of polynomials. And once you've done that, it all depends on the original topological triangulation you were given. So if you're happy with your bounds being on the order, being quite loose in this sense, being of this size, then you can get really powerful control over many geometric aspects of your hyperbolic manifold. So if you're happy with the looseness, the range of control that we have is really good. And so if you've got a problem that you could use this kind of loose but powerful geometric control on, please come talk to me about it. I would love to hear about it. Okay, thanks for having me.